You have likely heard the role of aerosols being mentioned in all sorts of things. Direct effects are, of course, when either the aerosols are absorbing and creating warming, or they're scattering and creating cooling, so-called solar dimming effect. We invoked the solar dimming effect for explaining the Indian monsoon trend from about the 50s to the 1990s, where the global warming should have warmed the land more because of low heat capacity, but actually Indian subcontinent didn't warm as much as the ocean, so the land-ocean thermal contrast is argued to be reduced, and that reduced warming or lesser warming of the land relative to the ocean was is blamed on aerosols and the solar dimming effect. You expect that even on a seasonal time scale, there are impacts of aerosols on the heating and land-ocean contrast and the mean monsoon. The question is, are the mean monsoon changes still manifest in the interseasonal variability and the active break periods, MISOs, right? There are two aspects to the aerosol heating in the Indian monsoon. There's a nice review paper by Bill Lau and his group which looks at the Middle Eastern Arabian heat low and dust loading and its impact on the monsoon circulation and monsoon rainfall. So you have the northwesterly shamal winds over the deserts which load up the dust to the northwest corner of the Arabian Sea, and that increases the heating, the land-ocean contrast, and adds to the Tibetan plateau heating and enhances or strengthens the low-level jet and the moisture transport, favoring excess rainfall or strengthened rainfall amounts in over the subcontinent. And the relation between the strength of the southwesterly jet and the rainfall is pretty strong. Okay, there is a second aspect to this western Saudi Arabian heating and dust loading. The monsoon itself is known to cause the so-called monsoon desert impacts, where the heating is diabatic heating is associated with Rossby waves and subsidence over the desert regions, and in addition to the Hadley cell, there is a contribution from the monsoon heating via this monsoon desert hypothesis, which can also add to the mechanism we just mentioned or enhance it in terms of the heating, the shamal winds, the northerly winds, and the Tokar Gap winds, and dust loading and the impacts here. Okay, so the other effect is more related to the Tibetan plateau heating and how that can get affected by the aerosol heating. This is a paper led by Jianqing Li, which summarizes the results from Bill Lau's group again. It's looking at normal water cycle, so this focuses on May-June, the beginning of the monsoon. In the normal monsoon, we have the gradient of the equivalent potential temperature, theta E, we have the low-level westerlies, we have ascent over the Indian region and descent over the ocean. We have the role of the Tibetan plateau heating. We won't get into the argument about whether the heating is important or the barrier effect is important and so on. But in this case, when there is aerosol loading in the pre-monsoon season, you can see that the equivalent potential temperature gradient is affected. The aerosol is resulting in solar dimming effect and cooling over here, and relatively enhancing the Tibetan plateau heating, and that's going to give you the relative cooling of the lower level and the heating of the upper level is going to give you this local enhanced circulation of the elevated heat pump hypothesis, as it's called, at the Himalayan foothills, and we'll see that in fact the aerosol loading can be maximum over there, as you can see over here. So this is an elevated heat pump hypothesis which has been debated now. Bolasina and Nigam argue that this doesn't work. Some other model results argue that this does work. One thing always key to remember is representation of the absorbing and scattering aerosols. versus the direct and indirect effects. We are mostly talking about direct effects. Indirect effects are much more complicated in terms of the impacts on cloud condensation nuclei, droplet sizes, amount of rainfall, cloud microphysics before that, and so on and so forth. So what we want here is a little bit more information on how directly MISOs or active break periods themselves, so they're not exactly the same as we already know. MISOs are propagating up here into the Bay of Bengal, and then there is the low pressure systems that are favored during the MISO that favors the active period. And here this is from the book chapter, but it's basically results from a paper by Manoj et al. Which basically diagnosed the impacts of aerosols by looking carefully at the break and active periods, and they found two cases. One was where the breaks were followed by active periods in this case, and there were also situations where breaks were not followed by active periods in terms of rain over the core monsoon zone. Okay, there are slight differences in so obviously you expect breaks to be followed by active periods, but not always in this case. Nonetheless, if you look at the aerosol index for the breaks followed by active and breaks not followed by active, there are differences, especially here, and you can see the loading here in terms of the differences. So the aerosol loading here is much higher, which results in a circulation that is feeding back, in the sense this anticyclone is going to favor aerosol retention and loading, and that's going to enhance the heating. So the additional heating because of this sort of aerosol loading is argued to be as high in terms of the land-ocean thermal contrast. It's argued to be or found to be as high as 6 degrees centigrade, which then favors the land-ocean thermal contrast, favors the southwesterly jet and the rainfall. So you have active period that follows here with enhanced rainfall. So the transition issue is there, and then the rainfall issue is there. Whereas in the case of breaks not followed by active periods, the circulation is still anticyclonic, and the aerosol loading is more concentrated over the eastern central Himalayan foothill parts, and this doesn't concentrate the aerosols as much over the monsoon zone. So the heating is much less by almost a degree and a half or so. So that land-ocean thermal contrast is not as enhanced, so that's why the active period is not followed. And this is the OLR difference, and you can see difference in OLR composites between BFA breaks followed by active periods and BNFA breaks not followed by active periods is positive, which means you have created this contrast of convection and rainfall. So the main thing to remember is that the aerosols diagnostically show that there is a transition from there is an impact of aerosols on the transition from break to active periods. Obviously during active periods aerosol loading has to be much less. There is the washout effect, so the transition from active to break is not so affected by aerosols, but that again depends on how the indirect effects on cloud microphysics and rainfall distribution or rainfall amounts and droplet sizes and so on are affected by the aerosols, which are not done very well still in the models, not at resolution required, at the resolution required anyways. Okay, so that's kind of the short introduction to the impact of aerosols on MISOs. We will look at the predictability of the monsoon. We already looked at that a little bit in terms of in terms of the intra-seasonal oscillations or MISOs being internal variability and affecting the seasonal cycle and making the seasonal cycle less predictable because of this high internal variability compared to the external forcing by the ENSO and so on. So you have to kind of bring all these together in your head in terms of intraseasonal variability being the critical time scale, and that being affected by at least the direct effect of aerosols as we saw here in terms of the transitions and the other effects that we have talked about. Okay.